Alright guys, happy snow day. I want you to watch the Minions clip first. It's like a 40-second clip because it's going to make you understand what we're going to fill in for the first definition. So if you haven't watched that, watch that. But I hope you're having a good snow day. So these are our notes about vectors, and if you watch the clip, you would have heard the villain vector say that a vector has both direction and magnitude. My other suggestion as you're watching this is to maybe be watching it on your phone and filling in your notes on your iPad so you have them filled in and you understand what's going on. So, this actually has a lot of physics behind it. Quantities such as force and velocity involve both direction and magnitude, so those are also considered vectors. What it looks like in picture form is what's called a directed line segment. So it's a line segment that has an assigned direction, and that direction is indicated by this arrow here. So in this picture, the initial point is P and the terminal point is Q, and that's how we're going to represent a vector. The magnitude of the vector would be its length. So the length is going to be the magnitude of the vector. And if two vectors are said to be equivalent, that means they have to have the same direction and the same magnitude. So we're going to learn a little bit more about these on the next page. So there's two different forms we're going to talk about that a vector can be put in, and this first one is the component form. So vectors can start and end anywhere, but if you put it in what is called standard position, that means you're starting the initial point at the origin, then we can use component form to write it in a simpler form. So a vector whose initial point is the origin can be uniquely represented by the coordinates of its terminal point, v1 and v2. This is considered component form, and it's written like this right here. So we're going to see those brackety things. They're like the almost arrowhead brackets. Those are what we're going to use to write a vector out in this form. So if we think of it this way, when we look at it in a second, v1 is the horizontal component because it's really the x-coordinate, and v2 is the vertical component because it's the y-coordinate. So if we go ahead and we graph this example here, what you're literally going to do is this is your x direction, this is your y direction. So we're going to go over 4, down -2. That's going to be our terminal point, and it's going to start at the origin. So that would be our vector. But again, the idea is that we have this x direction going here of 4, and this vertical direction here of -2. So it's really two components we're looking at. We're looking at a horizontal component as the first part and the vertical component as the second part. Then we have some notational things here. This is a new symbol you'll see. It's like double absolute value. That means they want you to find the magnitude of that vector. So if we wanted to find the magnitude, if you look at the picture I've drawn now, I've kind of created a triangle, which is going to be our goal with a lot of these, is we're trying to find this right here is the magnitude, which is really just the hypotenuse. So you can just use a squared plus b squared equal to c squared. We can use Pythagorean theorem to find it. So the formula for the magnitude here is it's going to be the square root of a squared plus b squared, where a and b are the two legs of the triangle. They're the two components, one being the horizontal component and one being the vertical component. Okay? So here is another example. This one is not starting at the origin. So our vector is going to have an initial point of over 4, down -7. 1, 2, 3, 4, 5, 6, 7. And over -1, up 5. So this is our vector right now. It's starting here and going to that point. We want to write this in component form, which means we would want to position it at the origin instead, which we're not physically going to move that, but we need to really think about what the two components would be to get from the initial point to the terminal point. So we're starting at that red point. I want to think about what my horizontal change would be. So the horizontal change is that it's going over 1, 2, 3, 4, 5. That's negative 5. You could get that same value from looking at these 2 points and subtracting them. We could take the terminal one minus the initial one, and we would get that same number. So the horizontal component is negative 5. The vertical component is how far it is that we're moving, again, from the initial to the terminal. So that one's I'm going up to get to that terminal point, and that's going to be up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Which you notice again, if we looked at the terminal minus the initial, I get that same value of 12. So my component form is negative 5, comma 12. If we had moved that up to the origin, that's where it would have, the terminal point would have been. And then we want to find the magnitude for that vector. So this is practice with that new formula. It's really just Pythagorean theorem. I'm trying to find the hypotenuse right now. I'm trying to find that hypotenuse side. So it's just going to be the square root of negative 5 squared plus 12 squared. So it's not really a new formula. You're just looking at the triangle and trying to find the hypotenuse. So that's square root of 25 plus 144, which is the square root of 169, which some of you may have known that Pythagorean triple already. That's going to be 13. And the magnitude should always be positive because it's a length, so it's never going to be a negative number. Alright, then these are just some examples visually of the vector operations we're going to do on the next pages. Scalar multiplication is when you multiply a vector by k. So you see some visual examples here of if we did half, it actually gets shorter. If we multiply by 2, it's going to get twice as long. If we make it negative, it goes in the opposite direction. And if we did like negative 3 halves, it's going to go out in the opposite direction and be 1.5 bigger. So these, all you're going to do here is you're going to multiply both components. I'm going to give you some notes here as we go by that number. So you multiply both components by the number. These are just the visual examples of what we're going to do mathematically in a second. So the next one is vector addition. If we wanted to add two vectors together, what happens is if this is the first one, if we were trying to do u plus w, would take this, you're going to take this v, and you're going to attach it on to the end point of where u started. V will start where u ends, which is what you see in this next picture. And what ends up happening is they form a parallelogram, but this is what we end up looking for. Again, in order to add those two together, if we're looking at it in component form, which is what we're going to get in a second, is we would add this horizontal piece plus this horizontal piece would give us the big horizontal piece for the red one. And then we would do this vertical piece plus this vertical piece, and that'll give me the big vertical piece for the red vector. So you're just going to add the matching components together. And you'll see this all on the next page. Alright, so then this is just an explanation of what vector subtraction would look like visually. So if we had two vectors, if we have u and we want to subtract v from it. So there's u, here's v. The first thing that has to happen is we actually have to create negative v and put that on the end of u. So negative v is how we would subtract it, would go in the other direction. So it's the same slope, same length, but it's going in the other direction. And then the result, u minus v, would be this red vector here. All that's going to happen is we're going to end up subtracting the matching components. Just like when we added the matching components, we'll subtract the matching components. So that's really the idea with the operations here, is you're going to match up the horizontals with the horizontals and the verticals with the verticals. So that's what this little end part here is showing you, is if we're doing multiplication, we're going to multiply each part of the component by that scalar multiple. If we're adding, we're going to add the first parts of each vector together and then the second parts of each vector together. And we're subtracting the first parts, which would be the horizontal parts, and subtracting the second parts, which would be the vertical parts. So here's an example. We want to... Alright, so then these are some actual examples with numbers here. So the first one, they want us to do 2v. So we'd take the v vector in the directions and we're going to multiply it by 2. So it's going to be 2 times -2, 5, which all that means we're going to do is we're going to distribute the 2 to both components. So it's going to turn into -4, 10. And then for part 2, we're supposed to subtract them. So it's W first, minus V next. And for subtraction, my reminder here is that you should distribute that negative. So I'm going to go ahead and distribute that through to both pieces. And then it's just about combining the like components. The horizontal components get combined together, the first parts, we get 5. And then the vertical components get combined together, and we get -1. So then the last one is supposed to be V plus 2W. So you're just applying these operations to the component form of the vectors, so times 2W. You do have to follow the order of operations, so that says we would multiply before we can add them together. So I'm going to multiply the 2 first, and that's going to turn into 6, 8, and then we can add them together. So we get 4, 13. Okay, the bottom part is just showing you the different properties of vector addition and multiplication. It pretty much shows you that the same properties that apply to algebra apply to vectors. It's commutative, you can change the order, you can distribute, you can apply the inverse properties, that if you add the opposite you get 0, if you multiply by 1 you get the same thing, if you multiply by 0 you get 0. So those are all what these different properties are showing you. Alright, so here is another way to write vectors. This is called the linear combination of 2 vectors, because what this is actually doing is it's breaking it down into 2 separate vectors. So you have an I vector and a J vector, where I is the horizontal component and B is the vertical component. So this is how I was getting you to think about it when it is in the bracket form, but this is literally separating it into the 2 separate ones. So if we wanted to graph this, we would actually graph this vector is just a horizontal vector. We're going to go horizontally -3. And then this vector is a vertical vector. We're going to go vertical 5. And our vector would be the one that starts and ends at that same spot, as that is going to be the vector they're asking you to graph. So the black one is the answer there. It also asks you to find the magnitude, which again, this is just finding the hypotenuse. So we're just going to use Pythagorean theorem. It's going to be the square root of -3 squared plus 5 squared, square root of 9 plus 25, which is the square root of 34. I can't simplify it, so I'll leave it, but if it is a vector or a radical that can be simplified, you should simplify it.